Okay, first about the homework, I heard that you have exams on Monday. Some of you also have exams on Tuesdays, right? Would you like the homework to be for Wednesday? Well, I also think that it makes more sense. I mean, you have exams on Mondays and Tuesday. You won't be able to do it, to work on your homework. Let's do it on Friday. But I will give you another homework on Tuesday. For the next Tuesday. So you will have homework for Friday and also 3 days afterwards. No. Well, you see, we started having the homework for Tuesday. Then we postponed it for Friday, sorry. Your homework was supposed to be for Friday at the beginning of the lecture. Then we moved it to Tuesday. I'm not moving it to Friday again. Okay, questions? No more questions during the break?
Can we calculate the potential of a uniformly charged ring, but not on the z-axis?
Anywhere. We can. I will not. I can calculate it approximately if you are very far away from the ring, if that will be enough for you. So this is the ring. Is it uniformly charged?
Yes.
So at a very far away point, the potential will be equal to, let's say this is R is the radius, 1 over 4 pi epsilon 0, 2 pi r lambda over r. This is the monopole term, plus 0 times 1 over r squared. The dipole is 0. Plus something like 1 over r over 1 over r cubed. We can calculate this coefficient if you are interested.
So in the fourth question of the homework, you asked us to calculate the potential of finite cylinder.
Finite?
I don't remember there is a word infinite.
What's the word?
Finite cylinder.
Finite cylinder.
Finite cylinders, how can we calculate them?
Well, you need to evaluate the integrals as much as you can. But I won't do it in the class. So you mean a square prism, infinite? Okay. No. You will still have infinitely many images. A finite number, I mean, you see, I can write down an infinite sum. No problem with that, but what's the point? And if I have a finite number of terms, then I can easily evaluate it. I can take the derivatives, I can study it, etc. But an infinite sum, well, even this, with the separation of variables, we also have infinite sums, but most of the time we can sum them up if we are really interested in it. But in this case, I'm not so sure whether we will be able to sum them up. Again, I don't think, if you are going for an infinite sum, I think the separation of variables would be an easier method to deal with than trying to identify infinitely many images. That problem you can solve by separation of variables.
There's a cylinder and shell, and inside there is a wire.
So you are saying that we have this cylindrical shell, infinite, and inside there is this wire. Shell is grounded. Shall we solve this problem? I mean, you see, there are two things you can do over here. This problem, you can solve by method of images because there will be one image outside. You can determine the position of this image, and then basically you are done. Let's solve this problem. So this is our cylinder of radius r. And we are told that at this point we have a wire, an infinite, this cylinder is grounded. The wire has a linear charge density, let's say plus lambda. And it is at a distance d. Now here I will have some other image wire with a linear charge density lambda prime. And the potential over there will be lambda over 2 pi epsilon 0 logarithm of r over r plus r plus over r0, let's say, some constant, plus lambda prime over 2 pi epsilon 0 logarithm of r prime over, let's say, r, again r0, plus some v0. This is the expression of the general potential we have. And what I want is, I want the potential at every point over here to be 0. So I have to choose lambda prime or this distance d prime suitably so that the potential on the cylinder will be 0. So let me rewrite this in a slightly different form. Let me say, no, let me keep it like this. And let me put the notation, this is r plus, this is r prime. Now r plus, this is the magnitude of the vector r minus d. Let me call this, r minus d, which is the square root of the square, r squared plus d squared minus 2rd cosine theta. Theta, this angle. This is my r plus. R minus, no, or r prime is similar, but this time r minus d prime, the magnitude. So this will be equal to square root of r squared plus d squared, d prime squared minus 2rd prime cosine theta. So v of r will be equal to lambda over 2 pi epsilon 0. Well, I can, by just choosing r0, I can just set v0 to be 0. By redefining R0, I mean, R0 just gives me a constant, the R0 terms. If you just write the logarithm as logarithm of R plus over R0, etc., they're just a constant. So by redefining, in a sense, R0, I can eliminate V0. So I will just set it to 0. Logarithm of square root of r squared plus d squared minus 2rd cosine theta divided by r0 plus lambda prime over 2 pi epsilon 0 logarithm of r squared plus d squared minus 2r d prime. These are d prime cosine theta divided by, let's say, r0. A priori, I don't know the solution. So let's just make a try. I will make a trial. Let's start by assuming lambda prime is equal to minus lambda. Let's see if it will lead me to a solution for d prime. So if for this case I can find a d prime such that this sum is independent of cosine theta, I'm kind of done. Now, if this is the case, v of r is equal to lambda over 2 pi epsilon 0, logarithm of square root of r squared plus d squared minus 2rd cosine theta. Well, on the surface, small r is equal to capital R divided by square root of r squared plus d prime squared minus 2r d prime cosine theta. I want this ratio to be independent of theta. Is it possible to choose d prime such that this ratio is independent of theta? That's the first question we have. Then, of course, we will discuss whether we can set it to 0 or not, or how we can set it to 0. Well, I can set this ratio to be independent of theta if I assume that r over d is equal to d prime over r. Well, the easiest way to see, in this square root, take the r out. In this square root, take the d prime out. There I have the ratio of d over r. Here I have the r over d prime ratio. These are the only, this is a function of r over d. This is the same function of d prime over r. So if they are equal, r over d is equal to d prime over r, all the angular dependence, it just disappears. So there's no angular dependence left. So, well, I'm done. This is r over d is equal to d prime over r, or d prime is equal to r squared over d. Well, this just looks like the expression in the sphere case. This doesn't look like the relation in the sphere case. In the sphere case, the image charge and the actual charge were different. Here, the image charge density and the actual charge density, they're just have opposite signs, same magnitude. This is how they are related, their positions. And, well, we know the image charge. Well, if you want to change the potential, well, actually, this is the only thing you can do. Well, for an infinite cylinder, you cannot actually set the potential at infinity to 0. So grounding, it doesn't really make too much sense. Grounding just means you are setting its value to the potential at infinity. So whatever the potential you have, you will have that potential. It is just, if you actually want it to be 0, just choose this V0. Or where is it? These two image charges, whatever potential they give you, just subtract it. It's a constant, you can subtract it, so that's it.
İki tane sonsuz varlığımız olsun, bir artı bir eksi.
Mm-hmm.
Bunlar da bir pol oluşturma.
You mean we have this here, there's an infinite wire, charge density plus lambda. Here we have an infinite wire of charge density minus lambda. Of course, they form a dipole. Their dipole, since their charge is infinite, their dipole moment is also infinite, but you can just like instead of talking about the charge, you talk about the charge density. Instead of talking about the dipole, you can talk about the dipole density. Linear dipole density will be equal to lambda times d, d being the separation. Or if you define this vector as your d vector, this lambda d vector, this is your dipole density, just as if they are point charges. But instead of charges, you use the densities. So instead of the dipole moment, you get the dipole moment density per unit length. Well, this exactly same problem you can also solve by separation of variables. Shall we also do separation of variables over there? Well, let's see. This is the problem we have. I have this infinite wire over here, this infinite cylinder, inside this infinite cylinder. So what I will do is I will first separate my region into two parts, inside this hypothetical cylinder and outside this hypothetical cylinder. The reason why I'm separating it, because both inside this hypothetical cylinder and outside the hypothetical cylinder, I have the Laplace's equation. So let's say this is region 1, this is region 2. Del squared V should be equal to 0. And V, I will use cylindrical coordinates.
Eğer çemberin tam ortasına olacak şekilde separatesi, yani temporalizm,
Well, I want to take Laplace's equation because I know how to solve the Laplace's equation, not the Poisson's equation.
Sağdaki zaten constant.
Hmm?
Yani sen de sağ tarafı constant.
No, it's not constant, it's a function. The Poisson's equation, that's a function. So here you see the charge density in this volume is not constant. It is 0 almost everywhere. Yeah, that seems almost like a constant, but at this point it's not a constant. So the function is not a constant. There's a charge distribution, which is not uniform. So that's why I would like to separate it into regions in which the potential satisfies the Laplace's equation. Furthermore, well, this hypothetical surface, you can just imagine any surface that you like as long as it contains this charge. Inside my surface and outside my surface, I will still have the Laplace's equation, but I mean, if I don't want to complicate my life, I should better choose a simple surface. So this is a cylinder in cylindrical coordinates would be a simple surface. So that's why I choose a cylindrical surface. Now the potential will be a function of only r and phi, r being square root of x squared plus y squared in this case, in cylindrical coordinates. And we know the expression for the Laplacian in cylindrical coordinates, which is 1 over r, del over del r, r del v over del r, plus 1 over r squared, del squared v by del phi squared. Since it doesn't have any z dependence, there is no derivative with respect to z, we make the assumption that this is a product of a function of r only and of phi only. We put this ansatz into our Laplace equation and divide by v. Well, let me divide by v later on. Phi times d by dr, r dr by dr, plus 1 over r squared, r d squared phi by d phi squared. This should be equal to 0. Now I divide both sides by 1 over r times phi, and we end up having 1 over r times 1 over small r d by dr, r capital R by dr, plus 1 over r squared, 1 over phi, d squared phi by d phi squared is equal to 0. Well, this is a function of the coordinate phi only. The rest depends only on r. So if this equation is satisfied for all values of r and phi, this ratio should be a constant. Furthermore, I also know that phi should be periodic with period 2 pi, because a given angle and that angle plus 2 pi corresponds to the same point. So that basically tells me that this 1 over phi, d squared phi by d phi squared should be equal to minus an integer squared. And we know the solutions, phi is equal to, let's say, a m e to the power I m phi. You are familiar with complex numbers, I'm assuming, right? So we know the solution for phi. Of course, the solution depends on this m, and since we are looking for periodic functions, m should be integer. M is 0, plus minus 1, plus minus 2, plus minus 3, etc. Let's look at the radial equation now. The radial equation is this one. Let us multiply with small r times capital R. And then we have, I'm also taking this derivative, r times d squared r by dr squared, plus, well, let me multiply by r squared, small r squared times capital R squared. So this will be r squared plus r times dr by dr minus m squared r. This is equal to 0. Well, we had already discussed differential equations of this form. You see, we have the second derivative multiplied by the second power. First derivative multiplied by the first power. No derivative multiplied by the 0th power. So the solutions of this equation will have this form, r to the power, let's say, n. If you just try this solution, put it over there, you would get n times n minus 1 plus n minus m squared. This should be equal to 0. Or n is equal to plus or minus m. So for a given m value, n is either plus or minus m. So the radial solution is bm r to the power m plus cm 1 over r to the power m. We have these two different solutions if m is different from 0. Because if m is equal to 0, we don't have two different solutions. We have a single solution, but there should be one more solution because we are talking about a second order differential equation. So for m is equal to 0, we have to treat it separately. Now for m is equal to 0, we have r squared d squared r by dr squared plus r, the first derivative. This is equal to 0. Well, I will just, let's cancel this one of these r's. What remains is d by dr of r dr by dr. This is equal to 0. Which tells me that coordinate r multiplied by the derivative of the radial function, this is some constant, let me call it b0. The derivative of the radial function is b0 over r, which tells me that for m is equal to 0, the radial function has this form, b0 times the logarithm of r plus c0. So we had to deal with m is equal to 0 term separately. Now we have the general solution. Well, there is the m is equal to 0 term. There is no phi dependence of the m is equal to 0 term. We have b0 logarithm of r plus c0. Then we have the m is equal to from 1 to infinity bm logarithm of m is equal to minus infinity to infinity. M can take both positive and negative values, we said. But m different from 0, bm times r to the power m plus cm times 1 over r to the power m times e to the power I m phi. This is the general solution in cylindrical coordinates. Now we had these two regions, region 1 and region 2. Well, let's look at region 2 first. Region 2 contains the point r is equal to 0. That is, if r is less than d, let's call that function v2. Well, at r is equal to r is equal to 0, the function should be finite. Well, that tells me that b should be 0, and all the c's should be almost 0. Well, let's see. Let's try to find a better way of writing the potential, because you see let's write it this way. This is C0 plus m is equal to 1 to infinity bm r to the power m e to the power I m phi plus m is equal to minus infinity to infinity to minus 1 cm 1 over r to the m e to the power I m phi. The positive powers of r, negative powers of r should be 0. That's why I wrote it in this form.
Şu D neresiydi?
Hı?
Hani D'den küçük değil.
D is the radius of this hypothetical sphere. Well, I will be slightly changing my notation. I didn't like this expression. No. You see, this is what I have, what we have. The same thing I can write in this form, b0 logarithm of r plus c0 plus sum over m from 1 to infinity bm r to the m plus cm 1 over r to the m times cosine m phi plus delta m. I just combine the positive powers and negative powers. This bm in that line is different than bm in this line. Let me just put that tilde over here. Then v2, R phi will be equal to B0 logarithm of R plus C0 plus m from 1 to infinity Bm tilde R to the m, no, this is absent, times cosine m phi plus delta m. This one. Okay, let me do it explicitly. I have this Bm R to the m plus Cm 1 over R to the m e to the I m phi term. I also have B minus m R to the minus m plus C minus m 1 over R to the minus m times e to the power minus I m phi term. Okay. So this is R to the mth power Bm times e to the power I m phi plus C minus m e to the power minus I m phi. Plus 1 over R to the m Cm e to the power I m phi plus C minus m e to the power minus I m phi. B to the minus m, right? No. You see, here I have the positive power of R. This is the positive power of R. So you see, this is a complex number that has a period 2 pi over m. Now this has to be a real number because we are talking about real potential. So this has to be a real number with period 2 pi over m. So I can always write a real number with a period 2 pi over m in the form of a coefficient times cosine m phi plus some phase plus 1 over R to the m. This here is also it has to be a real number, which basically means that B minus m is equal to Cm conjugate. This has to be a real number with a period 2 pi over m. So this is, again, some cosine m phi plus delta m. I can also argue that their phases should be the same. So this is why I can do this one. Or if you would just repeat our derivations over here, you see for the phi solution, I assume such a form m going plus or minus integers. I could have just assumed that phi is just a m cosine m phi plus delta m with m 0, 1, etc. So this is also a solution. I can write the solutions in this form also. I should have done it up there rather than confusing your mind, but at the end, this is what we would obtain. This is what we would obtain for the general expression of R and the potential. Okay, so this is let me just copy this. Then we just write the potentials in two different regions. And in the first region, basically I cannot really eliminate anything. You see, the first region is inner side of my cylinder out of this hypothetical cylinder. So in that region, V can have all the terms.
Hocam şuna G desek olmaz mı?
Why? Ah, yes. Why?
Şurada D sıfır.
Okay.
D var.
Yeah, on purpose.
O zaman şuna E diyelim. F olsun.
Hmm? Now then we have the boundary conditions. Well, the boundary conditions, one of them is V1 when R is equal to D and phi. This should be equal to V2 when R is equal to D and phi. These two should be equal. So this tells me that C0 plus n is equal to 1 to infinity of Bm R to the m plus Cm 1 over R to the m. These are D. Cosine m phi plus delta m. So I will put a tilde over here. That those phases can be different. This should be equal to D0 logarithm of R plus logarithm of D E0 plus n is equal to 1 to infinity Em d to the m plus dm 1 over R d to the m of cosine m phi plus delta tilde of m. This is one set of equations we have. On the left-hand side, we have a cosine series. On the right-hand side, we also have a cosine series. Cosine and sine series if you open up these cosines. So you just have to match the corresponding coefficients. So we have the condition we have from this equation is C0 should be equal to D0 logarithm of D plus E0. This is the term that doesn't oscillate, that doesn't have any phi dependence. And also we have Bm d to the m plus Cm 1 over d to the m. Cosine delta m should be equal to Em d to the m plus Cm 1 over d to the m cosine delta m tilde, and the same equation for sine delta m and sine delta m tilde. Well, the first one is the coefficient of cosine m phi, the second one is the coefficient of sine m phi. So basically these two equations tell you that delta m and delta m tilde, they should be equal. They should be equal, and what remains is Bm d to the power m plus Cm 1 over d to the power m should be equal to Em d to the power m plus C. I'm sorry, what did I do? I made a mistake somewhere. In region 2, I don't have these C's. Region 2 contains the R is equal to 0 point, so there are no C's. I only have this one. Bm d to the power m is equal to Em d to the power m plus dn m 1 over d to the power m. So this is one set of relations between our unknowns. And then we need to find one more set. And that other set of equations is nothing but E outside, the radial component, minus E inside, again the radial component, radial away from the center, should be equal to sigma over epsilon 0. Sigma now is a function of phi. We need to write sigma of phi. Now let's go back to our figure. Let me choose the x-axis to be from the center of my cylinder and passes through my infinite wire inside my cylinder. So this is my x-axis. So that the charge density is at phi is equal to 0. So sigma of phi is equal to some constant, which we need to determine, times Dirac delta of phi. This is the surface charge density on the surface. No z dependence. It's the same along the z, but it is non-zero only when phi is 0, and it is 0 everywhere else. To determine this phi, what you can do is you can just imagine some length of your wire. So let's see, this is our outer cylinder. Inside we have this wire, which has a linear charge density lambda. Let's integrate the surface. Now this is a surface charge density, so let's integrate over the surface of this cylinder. Over this surface. Now sigma phi ds, which is A Dirac delta phi. Now the surface of this cylinder will be, its radius is d times d phi times dz. This is the surface. And this should be equal to, let's say, a height h, lambda times h. Lambda times h is equal to a times d. Well, the phi integral just gives me 1. dz integral gives me h. So h is cancelled. A is equal to lambda over d. So we have the surface charge density as a function of phi. We know the potential in region 1 and region 2. So we can calculate the electric field outside our surface, inside our surface, take the difference, and then we should equate to this Dirac delta. And that will give us one more relation between our coefficients B, E, and D. So we have two sets of unknowns, two sets of equations, and we can solve it explicitly. Okay, I'm not interested in doing it. You are already getting sleepy following the derivation. It will be a nice homework after the exam. No. I'm just saying that since I'm talking about the surface charge density here, the total integral of the surface charge density over a given surface, it should be equal to the charge on the total charge on that surface. So that's what I did. I took this surface, only the side surface. There's a surface charge density only on that side. I integrated the charge density over that surface. That should give me the total charge on the surface, but that surface only contains a length h of my wire. And the charge of that length h of my wire is nothing but charge per unit length times h. The trick was, well, the one difficulty is how do you write that ds? For the surface of the cylinder, the surface element is the radius of the cylinder times d phi times the height dz. And then I evaluated that integral putting in sigma. Phi integral just gave me 1. A times d, they are just constants. Z integral, there nothing depends on z, and z I'm integrating over this length. It just gives me h. So I cancel the h's. So A just turned out to be lambda over d. So I know the surface charge density. Yes?
To prove that H is equal to lambda over D, can you start directly from the formula lambda H is equal to integral sigma ds? We don't do the previous steps.
Which previous steps?
I mean, we started, can we start directly from the formula lambda H is equal to integral? Yeah, exactly from here. To prove that A is equal to lambda over D. Sure. Did we use anything from previous steps?
No.
So they're completely independent.
Not really. I mean, you see, what was our purpose? Our purpose was to find the potential everywhere inside our cylinder that contains this wire. One method was the method of images. Well, that's kind of easy. So we said that, okay, if this is our wire, there is an image outside the cylinder, and so the potential inside the cylinder will be the same as the potential created by these two infinite wires. That was one solution. And then I said that since he was insisting of applying this method of images to a cube, and I was claiming that it's easier to use separation of variables in that case. So I said, let's apply the separation of variables to this problem, because you have all these different methods now to deal with the same problem. Method of images is one of them. Separation of variables in this example is also applicable. So what we did was we wrote the Laplace equation in cylindrical coordinates, and we found that in general, the potential in cylindrical coordinates can always be written in this form. This is the most general solution. Then, of course, since we are looking for we don't have a Laplace equation. We have a Poisson's equation. But we have this trick that if I assume such a surface, inside that surface there are no charges. So I have the Laplace's equation. Outside the surface, I have no charges. I have the Laplace's equation. So I know the solutions, general solutions. But these general solutions so here are the general solutions I have. This is the general solution in region 1. That this is this is the cylindrical shell. And the region 2 is the inner cylinder. So these are the general solutions in those regions. But I have all these unknown coefficients. I don't know what BMs are. I don't know what C0 are. I don't know what VMs, EMs, etc. I have to determine them somehow to be able to determine the solution. That's what I'm looking at. I want to find the potential. How can I find that? Well, I have to find some equations that they should satisfy. One set of equations I obtain by using the continuity of the potential. I know that the potential has to be continuous everywhere.
So why did we divide the cylinder into cylinders?
Because inside each one of these volumes, I satisfy the Laplace's equation. That was the point.
But the Laplace equation both of them is equal to 0, and both of them have the same charge. Both cylinders have the same charge density.
No, you see, those two regions have different boundaries. They satisfy the same Laplace equation, but they have different boundary conditions. So the solution will be different. But of course, there is a boundary that separates these two solutions. They have to be continuous across this boundary, the two solutions, because I will combine them to obtain a single potential for inside my cylinder. They have to be continuous, but their derivatives should be discontinuous. And the discontinuity in the derivative of the potential, which is the electric field, is proportional to the surface charge density. Now I need the surface charge density. I have to write down the surface charge density. I avoided it up to this point because I didn't need it up to this point. Now I need it. Then how can I write the surface charge density? On the surface charge is non-zero only when phi is equal to 0. It's 0 everywhere else. So the surface charge density has to have this form. Then the question was, what is A? And to determine A, I just assume that some surface whose total charge I know, h times lambda. And I also calculated the same total charge using this my surface charge density over here. This allowed me to determine what A is. Now I know the expression of my surface charge density. I know that my surface charge density. I just need to put it in this equation and obtain another relation between B is E's and these my unknown constants.
Surface charge density nasıl olduğumuzu anlamadım.
This one. Well, I know that.
Line üstünde sadece charge. Line üstünde
Okay. Yes.
bir şey seçiyoruz.
No, you see, this is my surface. On my surface, there is no charge in most of my surface. There is charge only when phi is equal to 0, there is some charge. Well, that is the property of the Dirac delta. It is 0 everywhere except on one point. So that kind of tells me that the surface charge density has to be proportional to this Dirac delta function.
Line üstünden bakıyoruz.
Yes. It doesn't have any z dependence because the line extends over all values of z. There's no restriction on z. The only restriction is on phi.
Tam ortasına bakmamız gerekiyor.
Why? You see, I already fixed my surface. My surface is fixed. I'm integrating over that surface, not some arbitrary surface. Okay, so they are about to kick us out. So see you tomorrow morning. Don't forget to come a bit early. So see you tomorrow. You won't need a calculator. Don't bring a calculator.